Hi everyone. As AI models are growing larger and larger, the energy required to train them is reaching astronomical levels. It's on track to require a gigawatt, the amount of energy consumed by a small city, by 2026. Can our current energy infrastructure handle this exponential growth, or is an energy bottleneck likely to slow down development? Keep watching to learn more. This video has 3 parts: the energy constraint, distributed power generation, and impact of green transformation. Part 1. The energy constraint. Right now, everyone is talking about how AI is going to scale beyond the current model sizes, or whether it can. Looking at past GPT models, we can see that the number of parameters is roughly 10xing every 2 years, which means that every 2 years, all the requirements go up by 10x. The amount of data you need, the amount of GPUs you need to train it, and of course, the amount of power needed to power all of those GPUs. I'll use numbers from Leopold Aschenbrenner's recent essay here. As a very rough guide, you have GPT-4 trained in 2022 requiring 10 megawatts of power, which means that by this year, we could expect to see clusters, AI training clusters, that require 100 megawatts of power. And 2 years later, in 2026, we could expect to see clusters requiring 1 gigawatt of power, and so on every 2 years. Well, many people hope it will stop when we get a large enough model to actually achieve AGI, AI that's as smart as a human. It may also slow down or stop altogether because we don't have enough training data, or the scaling laws just stop working for some reason. So these predictions are by no means set in stone, they're just predictions, but they're predictions with an exponential factor of 10, which is an extremely fast growth rate. Remember Moore's law that held for many decades, which said that computing power, like CPU power, was doubling every 18 months. And that effect of doubling led us from calculators to today's supercomputers. So it had a massive impact on the world. And that's only an exponential factor of 2. So you can imagine an exponential factor of 10 and the amount of rapid change that entails. So remember this growth rate, and remember the approximate order of magnitude power consumption of 1 gigawatt. Because in theory, you might have clusters requiring 1 gigawatt in the next 2 years, because it takes time to build a cluster. So if that cluster is supposed to be operational 2 years from now, that means it's being planned right now. 1 gigawatt, by the way, is enough to power about 800,000 houses, which is basically a small city. So that's a lot of power, and more on that later. But right now, the main question is, can our energy infrastructure actually keep up with this kind of scaling demand? Well, let's talk about current solutions a little bit. We've moved beyond AI companies simply repurposing existing data centers to train their frontier models. Starting with GPT-4, we had the new paradigm where you end up creating an entirely new data center just for training this new model. And the entire data center, the entire cluster, is utilized for training runs. And like I said, each successive cluster is going to be larger than the previous one, probably 5x or 10x larger. So of course you have to find enough GPUs and put them in that data center, but you also have to worry about how are you going to find and supply enough power to keep those GPUs running. One solution, of course, is to build your data center right next to a power plant. This is Microsoft's approach for some of their rumored data centers, to basically buy a nuclear power plant, or at least buy all the output from that nuclear power plant, and then put the data center right beside it. Of course, having your own power plant is really handy for load prediction. There's no other users of the electricity. You know exactly how much power you have, and therefore how much you can consume. There's also no overhead or interruptions from power transmission from point A to point B. And this is fine at the current scale, where 1 power plant is necessary to power an entire data center, but that probably breaks down when you have a data center that requires 10 power plants or 100 power plants. You can't build 100 nuclear power plants, right? Actually, you can't even really build 1, because a nuclear power plant takes at least 7 years from start to finish. Even China, which has a record of building nuclear power plants more quickly than anyone else, still takes 7 years to do it. And in the United States, there are 0 nuclear power plants being built right now. So you'd have to start from scratch, from year 0 of the 7-year period. This is a pretty well-known fact, and therefore it's something people bring up a lot in the context of powering AI. People say it takes too long to build nuclear power plants, therefore you can't power AI. But we'll get more into that argument a little bit later. I want to identify one other trend, which is an increasing push towards green power sources that are environmentally friendly. Some people, like Leopold Aschenbrenner, see this as an obstacle to getting enough power to supply for AI. I disagree with that perspective, and hopefully you'll see why by the end of this video. The answer lies with the electrical grid, which is basically the system that transports electricity from place to place and allows your house to actually have electrical sockets that you can just plug things into and expect electricity to flow. The electrical grid has been called the biggest machine ever created, and it's true. It connects every power generating source through tons of transmission lines that go between different cities, between different states, or even different countries, and then is connected to every single user of electricity, which is pretty much everybody. It's not a simple system either. Basically, the amount of power that's being used, the demand, is going to drive how much supply there should be. If you own the grid, you don't want to produce too much power because it's not going to get used and you don't really have enough energy storage to keep that around. So it ends up wasted. It's wasted money, basically. On the other hand, if you don't produce enough electricity, then some of your customers are going to have brownouts. They're going to have interruptions in the power supply. So you want a healthy margin. You want to supply more power than is actually needed, and you want to be very flexible for demand. So if demand is going to increase all of a sudden because people are coming home from work, then you want to increase the power generation capacity, turn on more sources of electricity, or configure the ones that are already running to produce more at once. The grid often has what are called spiking power plants, which are power plants that are off most of the time, and they turn on whenever there's a spike in the demand. Usually these are peaker plants, which are powered by natural gas, simply because they can turn on very quickly. So first observation is there's actually a fair amount of power available simply by turning on the existing power plants and the existing infrastructure. If you had to increase the power in the grid, you could also potentially turn on some plants that had been disabled for maintenance or political reasons. For example, California just voted to close their last operating nuclear power plant because they just didn't want any electricity coming from nuclear sources. And Japan is quickly closing all of their remaining nuclear power plants as well, even though it's a very important energy source for Japan because they don't have any natural resources, so they end up having to import in bulk oil from other countries. Though in Japan's case, it's a totally understandable reaction because they had the accident in Fukushima. The grid also allows for the construction of a lot of new energy generating sources. Sometimes the grid is wholly owned by the state in a form of utility company. Other times it's a little more deregulated and private companies can actually just show up and say, I want to sell you some electricity, what's your rate? And you can do business that way. So yeah, the grid is a business. People make money by supplying power, or the government makes a little bit of profit or balances the budget or whatever the case might be. That's why most people in areas with a reliable grid don't have any on-site power generation facilities because they don't need to. There are people that specialize in that and they do it really well, so let them do their business. Of course, if you live in an area with an unreliable grid, you might want to keep a generator on hand just for emergencies. I want to mention as well that the grid is constantly evolving. In the United States, the first grids were constructed in the 1880s, I think, and they've basically been machines constantly operating from then. You're seeing a push for increased electrification of all kinds of devices, from cars to appliances. This is because electricity is the most flexible form of energy. It can be a little more inefficient because you often have to, for example, burn gas in order to generate electricity and then use that to power a car. And if you just burn the gas directly in the car, then potentially you're capturing more of that potential energy. But by having power plants, you're centralizing the potential pollution and the management and the efficiency of the system in such a way that it can be easily upgraded, instead of trying to get the entire populace to switch from one type of engine to another, which is what London did when they basically said all of our vehicles will run on diesel from now on. So partially for environmental and partially for other reasons, you see a lot of increased electricity use. For example, in Oakland, California, you can no longer install gas appliances in any new buildings. They have to be all electric. So this is just a natural increase in the amount of electricity just from what people are already doing. On the other hand, you also have natural decreases, especially as new technology is created. For example, air conditioners are one of the most inefficient devices known. They consume a ton of electricity. There's a more efficient device called a heat pump, and heat pumps are slowly replacing air conditioners. Heat pumps are much more power efficient, and they can increase the temperature as well as decreasing it. However, as of right now, they're much more expensive. Nevertheless, they're already used in many places in Europe, as European countries, especially Germany, are trying to reduce their dependence on natural gas. So the long and short of it is that the electrical grid might contain the solution to the energy consumption of AI. So let's dive into it a bit more. Part 2. Distributed power generation. You might have heard that there's two major types of electricity called DC and AC. DC, or direct current, is basically all the electrons going in one direction and it's much more useful generally speaking. And AC, or alternating current, is where the electrons are going back and forth, alternating between positive and negative 50 or 60 times per second, depending on which country you live in. Right now, about 74% of the electricity that's actually consumed in houses is utilized in the form of DC. However, the power that's flowing through the plugs in your walls is actually AC. If you look at computers, for example, they'll have a plug to get AC from the wall, and then there'll be a power converter or a power supply that turns the AC into DC, usually like 5 volts or 12 volts, so that the appliance can actually use the electricity usefully. So why use AC at all? Well, the answer is because of power distribution. Although DC is much more useful locally, AC loses a lot less power when you transmit it over long distances. This was actually an argument between Edison and Tesla, the original Tesla, not the car company, when they were competing on trying to create the first grid. And Tesla actually won. He was the one who wanted AC, and it turned out to be a lot more efficient, so our grid is now built on alternating current. One of the main reasons AC is more efficient for power distribution, power transmission over long distances, is because you can step up the AC to a higher voltage much more easily. And the higher the voltage, the less power loss over long distances. So typically long distance power transmission is on the order of 100,000 volts or even 750,000 volts, which if it sounds like a lot, it is, since our plugs have like 120 volts or 240 volts in them. Of course, when you transmit power over long distances, there's still some amount of power loss along the way. The loss of power at each step is called the line loss. And you can break it down like this. You lose 1 to 2% when you step up the electricity in the power generation plant from whatever voltage it was at to a high voltage. You lose 2 to 4% during energy transmission at the high voltage. You lose 1 to 2% at the step down to a lower voltage closer to your destination. That's still at some power station, which has a lot of power infrastructure though, because you then lose 4 to 6% while you transmit the power at a lower voltage to substations and to individual houses and wherever it's actually needed. The lower transmission is done at like 2,000 to 35,000 volts. I don't know why they step it down that much, but it's probably for safety and cost reasons. Really powerful transformers are expensive. So the average loss between the power plant and the final consumer is 8 to 15%. However, if you have a data center or something else that consumes a lot of power, it's probably hooked up very closely to the grid. So you can basically exclude the last category. There's no last mile transmission costs, which means you end up with between 4 and 8% between the power generating station and the data center. 4 to 8% line loss is not that bad considering. The upshot of this is that power generation and power consumption don't have to happen in the same place. Power can be transmitted very long distances indeed. In fact, large regions of countries, or even large groups of countries, often have interconnected grids so that they can buy and sell power from each other. Europe, for example, is mainly one big grid, and in the United States and Canada, there's an eastern grid and a western grid, and also a Texas grid. Apparently, Texas didn't want the federal government messing with its affairs and dictating prices of power or things like that, so they opted to not connect their grid to any other states, because if it crossed state lines, then it became a federal problem, but otherwise it was just internal to the state. Of course, this is less redundancy, and it really bit them 3 years ago during the Texas power crisis, when the temperature became really cold and some critical component of a nuclear power plant actually froze and shut the whole plant down. They didn't have enough plants to bring up again to satisfy the load, and they couldn't bring in power from outside the state, so it led to a series of cascading failures that left everybody without power for a long period of time. When it comes to electrical grids, redundancy is always a good thing. In Canada, power lines were built north-south to allow Canada to sell electricity to the United States and vice versa. It's also split into the same eastern-western grid that the United States is, which is fantastic because Canada actually has way more electricity than it needs, at least in the province of Quebec, because there's a ton of hydroelectric power generation in the northern part of the province. So in 2020, Canada exported 67 terawatts of power to the United States. Its customers include New York City, which gets a large portion of its power from northern Quebec. Let's talk briefly about various different kinds of power generation with an eye to what would be useful when you're trying to power AI data centers. As I already mentioned, there's nuclear power plants, which usually pop into mind for some reason as a very reliable power source unless it's located in Texas, which can have constant output, which is great if you're running a big data center. However, because they take 7+ years to build, it's not really on the table when it comes to conjuring more energy generation capacity out of thin air. Of course, you have typical sources like coal and natural gas, which are pretty cheap and reliable and generate fair amounts of pollution. And of course, you need secure access to the fuels if you're going to try to use them at scale. Wind is great, but there's a lot of people that don't want giant windmills in their backyard, so they say, not in my backyard. It's a common response. You can put windmills offshore, actually floating on platforms in the ocean. So that's starting to happen more and more. Hydroelectric power needs rivers that you can dam, like I mentioned. You can get a lot of power out of them, but of course, only if the geography is favorable. You could locate a data center right next to a massive dam, take all the power from the hydroelectric generators. That would be a very good way to go. And then there's solar power, which mainly needs sun, of course, and land. You need a fair amount of space if you're putting a ton of solar panels in. Luckily, it's also not mono-use. You can grow crops underneath the solar panels. Australia lets sheep graze underneath their panels. And you can also put panels on top of water. For example, they do that inside of reservoirs in Singapore and Japan. Not only is it double using some wasted space, you get a dam out of it, and you also get more power from the panels, but the panels even reduce the amount of water evaporation from the surface of the water. Solar has one big plus and one big minus when it comes to powering data centers. The big plus is that it's very fast to build a solar installation. It often takes 6 months, maybe a year if it's a big project. Elon Musk famously put in almost 100 megawatts of panels in South Australia within 100 days. The minus, though, is that you need sun. So generally speaking, solar plants often operate at only 20% of their maximum capacity. So you have to overbuild and possibly invest in batteries to store power for non-sunny days. But we'll talk more about that in the next section. First, let's just go through some quick examples of what different amounts of power actually mean. An average house in the United States takes 1.2 kilowatts of power, which is 1,200 watts. So if you're talking 1 megawatt of power, that's about 800 houses, while a gigawatt is 800,000 houses, which is basically a small city. If you scale up to big cities, well, New York City uses between 5.5 gigawatts and 10 gigawatts, depending on the season. And the United States as a whole has 1.3 terawatts of energy generating capacity. On the power generation side, if you have a small nuclear reactor, that might be 200 megawatts. A really big solar installation could be 1.5 gigawatts. Same for a really large wind plant, although the largest wind plant is actually 8 gigawatts. Meanwhile, 5.5 gigawatts is the largest coal plant in the world. 6 gigawatts would be a large hydro plant, although the largest again is 11 gigawatts, and 6.4 gigawatts is the largest nuclear power plant in the world, located in Canada. Part 3. Impact of green transformation. When people hear estimates of 1 gigawatt, 10 gigawatts, 100 gigawatts just to power a data center, it's basically met with disbelief, right? I saw another YouTuber make a video that basically boiled down to, no one will build that many power plants. But I want to be clear here. People would not build such massive data centers if they didn't expect to make money off of it. They just keep increasing the investment because the previous one was very profitable. And there's very little people will not do if they have access to unlimited capital and expectations of return. If you have unlimited capital, you can build a 1,000-bed hospital in 10 days. China did that in Wuhan. You could create a vaccine against a novel pathogen in 10 months. Researchers did that with COVID. You can build 34,000 kilometers of high-speed rail. China did that between 2013 and 2023. You could even send a man to the moon in less than 10 years, which the United States did after President Kennedy made that commitment. Depending on when you're watching this, I suspect that NVIDIA might be the largest or the second largest company in the world, or maybe not, but probably still doing just fine for itself. And the other companies that we're talking about who might be funding the construction of giant AI training clusters are companies like Microsoft, Google, and Amazon. And they're no slouches either. All of these companies have access to basically unlimited capital because of their valuations. They can take tiny slivers of their equity and give it to other people or to banks and get as much money as they need. So are companies with unlimited capital going to sit back and say, gee, if I could only build this giant supercluster, I would make lots of money, but it takes too long to build nuclear power plants. I guess I'll give up on that. Of course not. If there's a way to do it, then they will. And here is one way that I'm pretty sure that they will proceed. I think the real solution is investing in solar and batteries to store power for those panels. Mainly because It's really, really fast. Like I said, you can build a small solar installation in 6 months. And with the grid, you can put those panels in a really sunny location, and assuming there's enough transmission capacity within the portion of the grid you're interested in, your data center doesn't have to be immediately right next to them. The main problem with solar is, what do you do at night? Or if it's not sunny, but we're assuming you're putting the panels in a really sunny location. So what do you do when it's night? Basically, you need a lot of batteries to store enough power for overnight. The best battery tech right now in the world is basically lithium-ion batteries. They have a slight tendency to explode in certain cases, which is why you can't take them on airplanes, but they're extremely effective, very energy dense, and unfortunately, very expensive too. There are some fun alternatives out there. For example, in Los Angeles, when they're getting lots of power during the day, they actually pump a bunch of water uphill to a reservoir. And then when they need more power in the evening and at night, they let the water fall down and spin turbines and generate the electricity again. Using a similar principle are gravity batteries, which are basically this big 15-ton object that is slowly winched upwards and then let go downwards when you want to produce electricity again. There are actually people buying old abandoned mine shafts just so that they can take a 15-ton giant object and lower it all the way down to the bottom of the mine. It's a crazy world. And Ray Kurzweil says that we're nowhere near the theoretical limits for how much energy can be chemically stored. And he thinks it's actually a matter of finding the right building blocks, the right molecules, the right polymers that, when put together, actually store a lot of energy. You might have heard of the protein folding problem, and this is kind of related. Basically, it's really hard to figure out in advance which molecules are going to work well in terms of storing energy and what the state will look like when they're in their lowest energy state, which is something you need to know when you're building batteries out of them. So probably, as we get more advanced AI, we'll be able to actually look at this problem in more detail and start figuring out more and more materials that materials science can use to then perform more and more previously unheard of abilities, like packing more energy into a small space or building a battery that doesn't cost very much. I want to note as well that a data center that's being used for training is not actually mission critical, in the sense that you could actually pause a bunch of GPUs overnight. Now, the companies wouldn't want to do this because they're basically getting half the value out of their GPUs, right? But in an emergency, especially if you're running low on power, then why not? We already do this for heat, right? If the computer is generating too much heat, it will throttle its performance. It will slow down. Well, you could easily do the same thing if you're running out of enough power to supply the whole data center. Okay, you might ask, all well and good, but could you actually supply a data center that needs 1 gigawatt of power, for example, by using solar? Well, let's do the math on that. To build a solar farm costs about $1 per watt on the high end. So for example, to build a 1 megawatt solar farm, you would need $1 million. That's US dollars. So to build a gigawatt, you would need $1 billion in theory. But like I said, solar panels generally only operate at 20% or perhaps a little higher of their officially rated wattage. Okay, so spend $5 billion. Now you're getting 1 gigawatt out of it, without any energy storage though. And according to a study I read, lithium-ion batteries are currently about 50 cents per watt hour, specifically $500 per kilowatt hour in 2022. That's actually on the high end. I want to use more conservative estimates here. It's also a nice round number. However, by 2025, the National Renewable Energy Laboratory expects up to 36% improvement in terms of cost per dollar for lithium-ion batteries. But anyway, we'll use 2022 numbers. Let's say you want to supply 1 gigawatt over 8 hours. Because it's 50 cents each, that would cost you $4 billion. I don't know how much energy storage you would actually want, 8 hours, 16, 12, but regardless, you could imagine that the total cost of the power for the 1 gigawatt data center would be between 10 and $20 billion. Assuming, of course, you can actually buy that many solar panels. But the good news is you actually can, at least if you don't care about geopolitical considerations. China is capable of producing way more solar panels than they actually are right now. There just isn't enough demand. But they're estimated to have more than 800 gigawatts of annual solar panel production capacity. That's right, 800 gigawatts. So you want to buy 5 gigawatts this year. Is that right? Suddenly that sounds a lot more feasible. Of course, for geopolitical reasons, China might not want to sell to the United States a bunch of solar panels that might enable the creation of a fancy new AI cluster. However, the United States is also ramping up its solar panel and battery production capabilities thanks to the Green New Deal. And also, it might be structured as basically, we're just upgrading our electrical grid. So it might be really hard to tell that this is actually what's happening. Is $10 to $20 billion outlandish for a 1 gigawatt data center? Well, at 1 gigawatt, you're already buying on the order of 1 million GPUs, which at NVIDIA's current price of $40,000 each is $40 billion. So if you're spending $40 billion on GPUs, then suddenly spending up to $20 billion on the energy generating capacity for that data center doesn't seem too out of whack. What about 10 gigawatts or 100 gigawatts? Well, the point is that this is the grid, and you can actually take energy from any sources as long as the grid infrastructure can support it. By no means would I expect that solar is the only energy source for any project of this scale, but I would expect projects of this scale to utilize the decentralized infrastructure that we already have in place, which is the grid, for managing electricity. I want to highlight two examples here as well. There was actually a proposal in the United States in the year 2015 to change the entire grid to be sustainable coming from green energy sources. It wasn't a serious policy proposal, but it was a paper by some researchers basically saying, hey, the problem here is not the technical feasibility, it's the political will and the amount of money, of course, required to actually commit to making such a project happen. I don't remember the timeline on that particular paper, but if it was 10 years, well, we've used up 9 of those years and we probably have done almost none of those recommendations, except the recent Green New Deal, as I mentioned, trying to invest in the infrastructure for green energy. On the other hand, there's Japan. As I mentioned previously, Japan is heavily dependent on energy imports. They get a lot of oil and gas and burn it, basically. That's how all their electricity gets generated. So Japan really liked the idea of solar panels, and they built tons and tons of solar farms all over the country. The problem is that solar uses land, and Japan doesn't have a lot of spare land. So they overbuilt solar somewhat. And rather than having a mix, which could also contribute when it's cloudy out, for example, they end up still having a really strong dependency on oil and gas. So really, when it comes to generating massive amounts of power, it's all about using the resources that are available to you, whether it's rivers, abandoned mine shafts, or maybe some oceans, or maybe some coastline that you can just float a bunch of windmills on. No one size all actually fits when you're trying to construct a grid. And I think the same thing is true when you're trying to construct essentially what is looking like a mini grid, right? A 1 gigawatt or larger power supply for a data center. Finally, in conclusion, we talked about the amount of power that would be needed if frontier AI models continue to scale at the current rate. We also talked about the conditions under which they would do that. Basically, is it likely to be profitable? And never mind the price tag. With virtually unlimited funding, these companies are going to find a way to build the energy that they need to power their data centers. They'll be able to leverage all of the existing strengths of the electrical grid, including generating power really far away from where it's actually used, and experiencing like 4 to 8% line loss along the way. So almost all the electricity actually gets to the final destination. They're also likely to invest a lot in renewables. I mentioned previously that data center companies really like green energy because it helps their image, but also in this case, it's really fast to build certain types of renewables, like solar panels. So that's going to be a key advantage in this race where everybody's trying to build the next greatest data center. So basically, in my opinion, there isn't really an energy bottleneck when it comes to AI development. If you liked this video, check out this previous one I made, which takes you inside a $100 billion next generation data center and what it would actually look like. And if you want to talk to me and my community, make sure to join our Discord. Thank you to everyone who supports this channel, and this is the last video that I'm going to film in this location. So look forward to a new background for the next video. All right, that's all I have for today. Thank you very much for watching. Bye.